Yeah, Frank, I looked high and low.
Just wait a minute,
for
guys.
dynamometer.
Yeah.
I could
Wait a
rent
minute,
one, I
guys.
could buy one, there's nothing out there.
Give me a neo-magnet. I'll show you something.
Which really surprised me, Frank.
Yeah, these little models.
I'm gonna show you how to do this, man. Wait till you see this.
Unless, model shops or something have them that do. I thought I saw one, but it was in a lab already. It was all computerized with digital readouts.
Yeah.
And then somebody told me about, well, can you use a clutch brake, they called it, and I said, I don't think so. It won't work the same.
We have electronic brakes. They really just
not gonna tell us.
slow down the motor
It is
with
gonna tell
constant
us.
current. That's all.
Where's the super glue? Go get some super glue. A neo iron magnet becomes an electronic brake to this. See? You put this on the scale, you calibrate the scale, right? And you push it till it's about 1/3 of the RPM, which you can tell me on the scope.
Gentlemen, I'm going to change tapes. Stopping tape. Okay, gentlemen, we're
And they'll
rolling.
come out in ounces. See here?
Okay.
It'll come out in ounce pounds. Oh, look, it's stuck there.
Ooh, that'll leak.
Let me get it out of the way.
It's going so slow.
Wait a minute. This ain't fine enough here, I need a fish.
No, I know. No, fish scales don't go to that, I already looked. Won't even give you what you want. That's, I think, the trouble we had, we couldn't, there's nothing fine enough.
Okay, there's one other way to do this. See, I'm afraid to do this because I
It
don't
could snap off, man, and go right
snap
to
off
it.
on.
And go right to it, you don't wanna do that. There you go.
I hate to do this. The scale's never no good after this, right?
Yes. So we are going to push it.
Well, I'm gonna push it.
In other words, you're gonna slow it down to 1/3 of its power,
Power by pushing it.
loading it.
Yeah.
You give that stuff time to set, John, otherwise it'll come off.
No, it scares me, but
Let
there's
it
only one way to do this. It's not gonna let you do it. Everything's powerful. Right? It's teaching and can't do that.
too hard.
We need a rope. We need something wind around the shaft,
Yeah.
right? And put your weight in the
Yeah.
1/8 pound. We got a piece of thread, Gary?
Yeah.
You would do it. I got it, thank you.
So then we have the friction.
Yeah, then we have the friction right here.
Okay. And then we can.
And you'll have to hold this end, Frank.
Okay.
We'll stop it just a second, okay? So we can get it around the shaft. You see what we're gonna do? Well, I'm gonna pull it.
Yeah.
I'm gonna pull it down on this side,
Okay.
and you're gonna pull it tight on that side.
Okay.
As soon as I get this around there. You're gonna pull it towards the ding end and pull it, all right?
Okay.
Get this out. And we're gonna get the inch point. Okay, so you gotta let it run, right? That'll get up to speed. So let loose. We want about 1/3 of the RPM. And now when I tell you to, what you need to do is hold this
Yeah.
right down to the table.
Okay.
And don't let it go. All right? Okay, and I'm gonna load it to 0.1.
0.1.
0.1 inch pound.
Okay.
0.1 inch pound.
1 inch pounds. Let's see.
Frank, the damn battery climbed upward.
Yeah, sure. If there's no current, then it will go up.
It's 0.1 inch pound.
Okay.
That's with all its load, right?
Yeah.
How we got it?
Got it?
Yeah, what we did was we put
I ain't found it.
this piece of string around the shaft, a loop, right? Frank held it, and I pulled this right up until it stalled the motor.
Got it.
0.1 inch pound.
Make your own little dynamo.
Yeah, actually what it was, Frank, was 1 ounce.
1
Yeah, see right there, it
1 ounce.
stopped right at 1 ounce.
1 ounce pound.
Yeah, 1 ounce pound.
Okay.
Yeah, that's the only way you can do it. One ounce pound. Now we need to convert that into pounds. 0.1, isn't it?
Well, an ounce pound, 16th of that is foot pounds,
Yeah,
and that's in work, but I forget what the conversion of joules is, but we can look that one up.
Okay.
That's the standard.
Yeah.
We can get there if we got inch pounds.
well, it should be in this book. The good old,
10.
maybe they don't
Okay,
teach this
10.
stuff.
10 Newton is round about 3.35 foot-pound.
Yeah. Let's see. It's hard to calculate, but once we get it, we got it. You know what, Frank, you just gave me an
Let's see,
idea.
we got an accurate time we started this, right?
Yeah,
Yes. Yes, we have timing for both of them.
So now the voltage, like I was saying, the voltage is increased on his meter. It's not a big effect, it's a small effect. I'm not hitting 11 or anything anymore, it's all down to 12. And that's what I would expect, because I want to know that other effect is in there, so it is. That's good.
let me just get past that.
That's good.
Here. Mechanical measurement.
It'd be in that once we got the inch pounds or foot pounds.
Yeah. We've got them all.
16 ounces are 1 pound. Yeah.
Yes.
Yeah. 16 ounces.
1 pound.
Then sometimes what? 16 or divided by 16
Is what?
ounces.
Right.
This one.
1 ounce. Right.
1 pound. Ounce.
Will be 1 ounce. Now see, you're an ounce pound, so it's 1 ounce. So 1 ounce, there's 16 ounces in a pound. Right? Am I right, Tom?
1 pound, 16 ounces.
Yeah, 16 ounces, you had 1 ounce pound. So you had 16 ounces, or 1/6, or
1/16 of that gives you,
yeah, 1/16.
yeah.
So we had 1 ounce.
Yeah, which is 1/16.
Yeah. Which is 1/16.
And then we should divide that, right?
pound?
Well, that'll give you foot pounds.
Yeah, that's what you want. You want
There's a
foot pound.
standard conversion from foot pounds to joule. That's
So
a standard work unit.
What foot pound or?
Well, we got
I'm missing-
1/16 of a pound,
Yes.
right? So now we need to divide this and get foot pounds. So 1/16,
What is foot pounds? All force.
I'm trying to get where we got the foot, is what I don't see.
Right, right.
We
Where
just
do
got
we,
the force that
where-
withstood
yes,
to stop it, which is a standard measurement. Now, how do we convert that to, let's see, we've got a standard force. I don't know, I have to think about
foot pound calculator. Inch pounds to foot pounds, conversion.
that. Oh, it's the inch and the foot, we can't find out how to get.
Well, right here, I got it.
You found it on the internet?
No, they did a preliminary measurement with a little scale there to get the pounds pressure it takes to stop the thing from turning. It tells you what, it's exerting that
Right,
much force all
right.
the time it's turning, see, it's turning.
Mhm.
So you know how much force you're applying for a length of time, but that's impulse carried through, so.
yeah.
So, once we have the impulse, how do we convert the impulse into work? Normally I think have a mass or something. to make
Well, I
it-
know how we do this.
And I got the force. I have a mass inherent in the force.
Friction, rope friction.
Force.
Well, it's friction. It's-
One ounce.
Yeah, go get that big scientific
And
encyclopedia. We'll get it right. We're real close now. This is hectic stuff to do, but it'll work.
Yeah, so we have the condition of,
This is only the 5th edition.
Well, we'll get another edition of this. Look up torque.
rope friction.
that's essentially 1.2 pounds of force that's being exerted by that machine all the time to do the powering. So that's the work out. I mean, that's a force out. The time is 193 minutes. I can get an impulse that way, force times time. How the devil do I get that into work?
This here. Boy, that's a must, you know that, Frank, to find a dynamometer.
Force times
Yeah.
time.
Well, like I
Yes.
said, the big,
Those model stores, those, which one would be, where you can buy these little model airplanes.
Yeah,
and so on.
well, they ran that guy out of business.
I went to Motor Electric, who actually rebuilds electric motors. I went to, and you know, the only place was a Granger catalog, but that was an RPM. It reads RPM,
Oh, yes.
and which couldn't help us. No.
No.
And some guy, we found, builds custom ones, they're tailored. He said they run about $10,000. And well, you know, Frank, this is what we were running up against. And he said it'd be 2 weeks, 3 weeks, 4 weeks,
And then it
nothing on the shelf.
and
you
it
could
would
buy.
read what?
And it would, I mean, they would tailor it to try to read what you're trying to do. Which would mean they have to calibrate and
Yeah.
you know.
Yeah, there's something else in the dynamometer that uses it, enters into calculation, we don't have. I don't know what it is.
Well, you usually get pretty
Get
close.
the impulse, but I can't see how to get the joules out of that.
Well, leave it to good old Ron Cole.
Yeah, if possible. I agree, if possible.
Thank you, Ron, you were with us today.
Problem with all them converting factors, you know, they basically it's something like converting from English, British units to engineering units to metric units and things like that.
I think I threw this stuff away. I got a mistake for you. He did all this, Gary. He worked all this out one time. And I would never throw it away. Bicycles. Okay, you had 1/16 of a pound of 1 pound.
So we have a rotational torque,
Right.
which is power divided by omega. How do we go from there?
And all these
It's already
numbers.
in meter.
RPM value shown. Our shaft load value is 6.6, 66.6 of the free running RPM. Shaft load values. So if that motor is running at 3,000 RPMs, you want 66% of that,
It's about 2/3.
2/3. Now, Frank, we need to hook up the scope to the motor and by the time, figure out the RPM.
Can you do that?
Yes, do anything.
So we have
So when we use your scope, right,
how,
when we go across the collector to the emitter and you'll get a time in milliseconds, right? So we want to bring it in closer. Actually, maybe we want to expand it out. We need that goddamn techie scope.
they don't like my scope.
No
They
swearing.
don't like it either.
No swearing.
Can I sell you on a techie?
Sure.
Well, I tell you what, I will get it here.
Is Frank's scope fast enough to catch that, John?
You know, the only scope that's fast enough to catch this is a tube scope. It's one of these kind of scopes.
So, just, I have it.
See, a digital scope is great if
Okay.
no,
No, no, that's one.
okay.
I,
I'm just gonna set
yeah,
this.
no, it's,
Want it on the rolling chair there?
Yeah.
oh, no, let's sit there.
Right here? Yeah, we need the probe right here. We need your probe in your scope.
Okay. I have another probe here.
Okay, Frank's got one out there too.
That's a 100-to-1 probe.
Okay, fine.
Does that matter?
I've got a 3-to-1 adapter if you'd like to increase power. Will you?
Go ahead.
Thank you.
Okay, well, you already got this probe. Okay, so you want to put that one here, right?
Are we in business here? This one hour. Over an hour already.
Already over an hour, huh? I said 1.6. Here you go. Here is your time. 11.39. There's your time, right there.
Okay. Yeah. I have this time as well.
Well, this is these scopes are much better, right? A digital scope's got time delay.
Yeah.
You know, digital's a buzzword.
Yeah.
It's
It's good
kind
for
of,
certain
you
applications.
know what digital is? This is digital, Gary.
I know.
Right here. Here it is. Okay, I'm gonna take this off here, Frank.
Oh, jeez.
Before we break it.
Gentlemen, I got some, I inadvertently stopped the tape when I was switching gears
It's okay.
here. It's back on now. I don't know how long it's been off.
Okay.
Right?
Yes.
You wanna see how close I was to it? You're gonna love this. What did I say? I said 12:13. And now, and you're at 12:10, 12:09.
Yeah. Yeah, that's kind of predictable.
Yeah.
On this one, on the voltage itself, yes. Yes, it is.
That's pretty good though.
Mm-hmm.
There.
Thanks.
I guess Johnny knows what's going to be. Okay, I calculated 1.6 hours.
So,
1 hour, 6 minutes.
let's take worst conditions.
What is it? Yeah, I got 8 foot-pounds per minute. That's joules per minute. We can turn that into joules per second. Multiply by the number of seconds or number of minutes. We know the number of minutes we got. So that's 8 foot-pounds per minute times 180 for the 3 hours. Well, no, it's how long this one runs.
Yeah, it's how long
We gotta
this
know
one
how
is.
long it runs before we can finish that.
Okay,
Before you can calculate it.
this is the thing. I have calculated that that battery would only last 1 hour, 6 minutes.
How long have we been running? We've been running close to an hour, I guess.
We've been running 1 hour, 10 minutes, 12 seconds. And we got about another hour to go, Frank.
We still sat at 12 volts, John.
No, we're at 11. Well, yeah, we're gonna charge up, but well, I said that we would end up with 12.15.
So John was getting a rough estimate.
Yeah.
Of what he assumed.
Yeah, I went over to the
Yeah.
computer and
This is not-
calculated.
This thing I worked out is 8 feet per minute. It's not 8 foot-pounds per minute. That's not too bad an estimate on it, so.
Yeah,
That's, you can get from there in other ways. You get to take the radius of the shaft and constant pressure and all that. And convert it into RPM
Right.
and all that stuff.
8 foot-pounds, okay. Let's take the worst condition.
okay, take the word.
Let's say there was 20% left in the battery before we started charging.
Okay,
I'm sorry.
he wants to, well, explain it to Tom, Frank, 'cause I'm sort of lost when it comes to that one.
No, we don't know exactly how much charge was in the battery after we discharged it. So,
Some, I don't know how much.
yes, as we rapidly discharged it, it's probably still, let's say in worst case scenario, there would be 20% left.
That's about right, the worst case scenario. That's past discharge, yeah.
So the battery had 20% charge when we connected it and were starting to charge.
Right,
Then we charged it for 3 hours and 13 minutes. And then this should run for
1 hour, 6 minutes. I calculated it. It's way over that now.
It'll come out, I think Frank's getting that.
Yeah, Frank's got it.
Yeah.
You did it. It's been running, Frank, 1 hour, 12 minutes, 33 seconds so far. It's at 11.13 volts.
Well, we need to go 20% more than
yes.
1/3 of 313.
Yes.
That's about the simplest way, I guess.
Well, yeah, Frank's taking worst scenario. I mean,
Worst scenario. would
yeah,
be-
that's fine.
Well, it looks like,
Worst scenario is, let's see,
1.6.
3 hours, 13 minutes, 20% is 1/5 of that.
Get 120 milliamps, Frank,
1/5.
right?
Yeah.
180.
That comes out to be 1.6 at 11 volts, where I
1/5
took
of
it
that
from,
is,
Mhm.
in hours. You follow me?
Yes.
You've already been
almost 40 minutes,
1 hour, 13 minutes.
almost right at 40 minutes,
So 1 hour, 40 minutes.
we need to run our break-even point, allowing the worst case 20%, in that battery, not counting that,
Yeah.
throwing that away.
Yes.
Our worst case is 1 hour, 40 minutes.
Well, you're at 1 hour, 13 minutes right now.
Yeah, I know, we closed in on it.
Yeah. So,
So we need to let it stop, huh, Frank?
Just let her run a while,
Yeah.
if she runs a little while.
You're already up to 54.15 microamp hours.
That's with the worst case scenario. And then
so
that's
it's
what-
it's integrating.
Yes, it's integrating.
Micro amp hours.
Yeah. That's what you wanted it to do, right?
Yes. Yes.
The machine works, Frank.
Well, we want to take the conservative estimate, and Frank's right.
Yes.
That's, we better to take that conservative estimate.
Yes,
We don't want to pat ourselves on the back
No.
if something doesn't come out on the bench, and that's a good way to do it. I like that.
So
That's a fair case.
until we have more data in comparison, let's just get a starting point and then take
Let it
that
go.
as our benchmarking and try to compare
Sure,
all
sure,
the
sure.
others.
We do.
Let's
all the
go.
other tests.
So we need to watch this thing real careful.
At 1 hour, 6 minutes, that battery should have been at 12, 16.
It's about what it is.
That's right. So this will go almost 2 hours before it dies,
And that's enough.
which means
That passes your.
that that battery, for wherever state charge it was at, has over the charge.
Yeah, what it means is for the total thing that we put in the batteries, we give the 20%, that was
We
your
give it
charge.
up,
We
right?
give that up.
We give it up.
We have to give that up because there is a residual.
Right, so we
So
subtract
we
that.
do a conservative thing and say, okay, let's give up the full 20%. If we run an hour and 40 minutes, at that point we break even. And anything past that, significant repair, you know, we don't want to talk about seconds or something. But anything significantly past that
Right.
proves the purpose of.
Frank, you want a cup of tea?
Gentlemen, we're
Nothing changed?
No.
Thank you.
Okay.
At an hour and 15 minutes, right.
I think that's about right.
Yeah, but go look at the clock.
Well, yeah, Frank's got it written down
Yeah,
there.
Frank's got it.
He the official timekeeper, so.
Yes.
So we are at 1 hour,
Frank says
18
it's
minutes,
over.
21 seconds right now. I think you're right, Frank.
So even if it has 25%, let's
Still down home.
let's see how long it takes.
Yeah, write
I
it all
think
down
we
now.
have still another 30 minutes left.
Oh, yeah, easy.
Yeah. So then we can really say, even if it's whatever, 30%.
It's gonna come out to be
Well, the
160%.
better it comes out, the more confident we are in the measurement.
Well, the
We
more,
give up 20%, no problem, throw that away, and let's see how much over we go. And
Okay.
That means more
and
confidence.
then let's see what we get out of that one that we did
Yes.
charged, right? Because that would be the balance.
So that, he's got it lined out to
Frank, how'd you get that thing to integrate like
roll it
that?
in. It's in that corral there.
Frank, how'd you get that thing to integrate like that?
Yeah, it has an integrator.
All right, we gotta get further.
It has an integrator, so you can accumulate things. And this could be harmonics.
You know,
depends on
well,
whatever.
what's really surprisingly funny about this is it don't lose fast after you do it.
Yeah.
It's just like sustain. See, because at your break-even point, you're already an hour and 19 minutes, 47
That's
seconds.
right.
Do you know why it's going slower? Because the current decreases.
Okay.
So once the voltage drops,
The more it goes, the better.
The more it goes, the better?
Right.
yes, no. Actually, the less current it draws, of course, the slower the battery is draining.
Good. But the battery should only last in 1 hour, 6 minutes.
6 minutes, plus the residual charge,
Yeah.
which we can estimate to be somewhere 20.
So that would make it 1 hour, 16 minutes.
Let's even say if it's 30%, can we go past the 30%?
So we want to
Sure.
go past, we want to go till the thing stops, but let's hope we go past or even 30%. Then we're down home free. We've got high confidence in that.
Right.
Okay.
That's what.
I'm leaving.
So that's
I
what
believe
we
it's
need
gonna
to do.
that. I believe we're there.
Well, it's at 9995 right now.
But we will see that. We will see it
And we will do
in
some
the instruments
control
and measurements
measurements.
as we go.
Well, I made an hour, 21 minutes. So I went past it.
Let it go all the way it'll go, because we need that after we subtract, whether we want to subtract 20 or 30, whatever, be over conservative. We need to have a good, solid, high confidence measurement, and that's good. The further we are above that, the more confidence we have in it. Yes.
Here, Franco.
It's the old thing of trying to measure 100 volts, you know, when you measure 101 or you measure 99, you need a good instrument, okay, that's not
That's
too
good.
quick.
8.9 and 80 milliamps, 1 hour 22 minutes.
Well, we tried to find that dynamometer, but we
Oh, geez.
struck out completely.
We're short.
I looked for several hours there. And all kind of stuff. If you want a big one, you can get it,
A big one's not a problem for a car, for a big motor.
Little bitty dynamometers are a problem.
So we need,
And the funny thing was, the mention I found them was in Germany.
I'm going there next month, so I can look
Yes, that would be great.
at least.
We're gonna need one
at least
anyway
half.
for the lab,
Yeah,
because we'll be moving on to the next model. We gotta get going in the refining process real quick.
I like that power analyzer. I think that's
61.4 microamp-hours. Is it saying? Microamp-hours. Doesn't. It's not good enough. Microamp-hours. So it's analyzing maybe just up to the whatever fifth harmonic. That's where most of the power is.
Oh, yeah, it is.
So it's going fast.
Come on, Dottie.
Going fast. Now it's at 80
No,
milli.
no, let it go, John.
I
At
know, I
80
know.
Longer it
milliamps.
runs, the better.
Well, yeah, I know.
We can wait.
Hour 24 minutes.
What's your cup on the end of the table?
Let's see.
So then we are going to regard this an almost empty battery,
Yep,
which we can use maybe tomorrow.
yep.
And then we have one left here,
Yep.
number 2. And this one takes another. We need to monitor a little bit the current to get the average there. But we are now discharging for
You know what, the power
1 hour.
doesn't matter exactly.
a little bit over an hour. So this will take until 6
Hour and 25 minutes.
$6. That's what you're thinking?
4 hours, yes. This draining of this battery is designed for 4 hours, yes. But it doesn't need to be recorded.
You know what's unusual about that
Okay.
battery, John? Is it like...
Well, I'll go as long as I can.
Gets
I've got an hour and a half more.
Like it gets a flash of wind.
Would you like me to
as
save
when
some
you're
for the end?
tired. Yeah, just keep going.
So that we have, so that maybe
But
we
that's what you
summarize and we'll have all the
That's what you want.
conclusions.
It's up to you, Frank.
There you go.
It's your call.
Yeah,
Your call.
whatever you'd like to do.
Okay.
So you could do
I'll
that.
shoot all my tapes except for 30 minutes.
Save it for the end, so Frank, that way he actually knows.
Yeah, very good.
Well, if it's the same thing going on and you come back in later, you know, you're okay.
Yeah,
Nothing has changed.
Frank will know because he's
That
here.
curve continued, and Frank was here watching it all the time, so there's no problem.
Good. Yeah.
What we don't want is a whole bunch of time when if Frank weren't there and didn't know what was happening.
Right.
Then we need the camera showing what's happening.
Right.
Right, I agree.
Hour, it'll be an hour and 30 minutes when it's
30
done.
minutes.
Yeah.
Little mistake in our calculation. The 20 or the residual charge is of the total hours. So if you convert that to the total hours, normally one battery fully charged would run for 4 hours. If there's 20% left, it would be 20% of the 4 hours.
Well, see, the other one that ran the motor ran how long when we ran it down the first, how long, we ran 3 hours and 13 minutes.
3 hours and 13 minutes with
Okay, so,
a battery where we don't know where the charge was
Yeah.
at.
but when this one cuts off, it should have about the same residual in it that other one had that ran the motor the first time. The residual should be about the same. They should cut off at about the same point.
Yes, that's for sure, but we are charging this battery, so we don't have.
What we can do is, let's see now.
Can do a couple of things. We can use now this battery and determine its charge by discharging them, because at the beginning it was almost empty. So we discharged it over a period of around about 4 hours, which means the residual charge would be around 10%. But concerning the minutes here, what I'm saying is this battery, which we had previously
Charged.
first discharged at
Yeah.
a high rate,
Yeah.
so we don't know how much percentage was left before we charged it.
You mean, okay. So we subtract 20.
But 20 of the total time. 20%, so a fully charged battery would run the motor for 4 hours. Which means 20% would count towards the 4 hours. Would be 1/5, which
Let me
is,
take a minute. Give me
Well-
just a minute to reflect here.
We're an hour and 30 minutes and it's still running.
Let it go.
So-
A fully charged battery, drained down to some residual left in it, would run 3 hours and 13 minutes. Okay, that's a clear point. We got
Right.
that one nice.
Well, that's exactly what it ran.
Okay, so if this battery represents what 3 batteries would do,
Right.
Chihuahua.
we know,
I know what we should have done, but we didn't do it.
Yes.
Now that I see, we should have taken all 3 in parallel and run that.
we did.
But that's a long test. It's a long test.
Yes.
Well, that's what I suggested.
Yeah.
Yeah, that's probably.
But this
Okay,
is how
where
you
we are
do
now,
this.
we're running a battery, it's gonna run down to the same residual, so at least we know the residual is gonna be the same, we can come
Right.
from there.
Okay,
But we've
Jay,
got measurements on what's actually put out down to that residual. We're measuring this on the instrument. So if we take those measurements, we have the actual joules that that thing put out. We can convert that to what it actually furnished.
Yeah, I was trying to approach it.
okay, do
from
this
different
one
angle.
little, do this one little calculation first.
We have it, we
We
have it.
charge
down.
3
We have it down.
batteries
We
at
can
the
get
same
it.
time.
Yeah.
We
See?
need one primary battery ran 3 hours and 18 minutes total. right? Wasn't that true?
313.
313. That's
If-
one battery.
If the
Right.
battery would be fully charged, it would run for more than 4 hours.
That's saying that the battery is 100% efficient and they aren't.
No. We took the battery out of the package.
Right, but we don't know if it was
We
fully
don't
charged.
know
So he's
the
saying-
charge itself.
Yeah.
We know that a fully charged battery
Should have ran.
runs
Okay.
4 hours.
Let's-
That's what we
Let's
did
take,
last time.
let's take this figure. We used one primary battery.
Yes.
It lasted exactly
3
3 hours.
and 13 minutes.
Okay. You're now at 1 hour and 32 minutes times 3 is how many hours?
Yes,
That's how much you're over. Plus you got this one,
yes. Plus,
right here.
but
The one that's being
we
charged
still
now.
don't have the remaining charge in this battery before it was
That's
charged.
313,
Yeah, well, I'm getting this close. And then subtract,
193 minutes.
subtract your figure, right?
Yeah,
And you should have,
That battery went down like this.
Very close.
Residual.
add your work.
Residual.
yeah. But in all cases, we are neglecting the
batteries.
mechanical
Yeah.
work which is done.
Okay, 3 hours, 1 hour and 33 minutes. That's 4 hours already.
Yeah.
So Radio Shack had a partial charge in the batteries.
Yeah. Which is,
It's
I
not
think,
too bad.
correct for lead
For
acid
4 hours,
batteries,
3
they
hours,
are.
13 minutes is pretty good. That's about what the spec was, it's not too far.
Yeah.
Because that's the standard discharge rate they have there too.
Right now,
We're not quite at that exact rate, so our discharge rate.
Well, it's
is
pretty
not
close,
at the end of
Frank.
that curve. Residual, that's
Let's,
the same.
let's do
residual.
worst case again.
here we go. Come on, Frank.
Yeah, and go from there. And
Okay, we have a measurement. Let's see. The residuals will be the same. If it were all 3 batteries doing this, the residual would be the same when they got down there. So we have to back up from the residual. But we have measured what it put out. We're measuring it now, what's going down to that residual.
Right.
So you'll know exactly how much this one battery put out getting down to that residual. And we have 3 of them.
Right,
So 3 would put out 3 times that much.
that's right.
The residual is, we have to have some feel for
in accordance to this
how that corresponds to.
Yeah,
table, it's 10%.
Yeah, something like that. We need to go over 10 or 20%, we say. The combination of the 3 needs to be 10 or 20% more than the single battery performance
Yes,
because of the residuals.
yes.
okay, we knew how the primary battery performed.
Yeah, so I think we're gonna have enough to see that. I think we're gonna have enough to see that.
Well, you're at 1 hour.
If it runs
30
long enough, we really got it.
Yeah,
Well, you're at 1 hour, 35 minutes and 25 seconds, right?
Getting there, it's getting there. I get excited when it goes over 1 hour and 40 minutes.
yeah. So let's do worst case calculation.
See, I was trying to be very conservative.
Let's say
I wanted to safe side it.
it had 20% charge left of the
Just like hold this charge.
not this one, just after, before we charged
Where are we
it.
at now on time, John?
1 hour, 35 minutes and
We're doing
53
good.
seconds.
We're doing good.
Well, it's already, if you calculate the 3 batteries.
Yeah, but I gave that percentage correction. I took that 20% off of that.
Yeah.
I'm doing that. I'm safe side now.
Yeah, these are the numbers that she kept. I didn't think you needed to be correct. Yeah, these are the numbers. They're not clear.
Look, Tom,
Still there?
well, that's what I said, we get you very close there.
Yeah.
That's
Well,
it.
let's-
Would go
see,
1 hour.
We're gonna run this thing till it
Nice.
does what that other one did,
Yeah.
till it stops there.
Yes,
We have to do it to the same residual.
yes.
Yeah.
Otherwise, we don't have a same point on it to start from. But if we get to that, we've got a same point on that.
37.
We're doing good.
So in accordance to my calculations, the break-even point would be 1 hour and 52 minutes.
Okay.
Most conservative.
Most concerned. Okay, let's go for that. Then. Let's see how we do here.
Well, you still have to take and count this battery. Because you ran this to residual.
Yes, yes.
So whatever left over in this battery, when that one dies, you have to put that there and start the clock. You have to add this together.
Are we charging another battery?
Yes.
Oh, okay. Then we've
Yeah.
got to count that. Yes.
Yes, you got to count it.
That's a one. Cause we
That's right, so
we
if this
run
battery,
three batteries,
if
we
this
have
battery
one more.
goes 20 minutes,
Yeah.
this
We
20
gotta,
minutes.
we gotta take whatever that goes to residual and multiply
Yeah.
that by 3 and add that, that's a credit to us, okay,
Yeah.
that's no problem, that's good, Frank knows that, that's fine.
Well, you're already,
I didn't realize you had another battery in the circuit.
oh yeah, right through the battery in there.
That's good, I'm glad he did.
So this was our discharged primary
Yeah.
Yes, that's good.
where we know that can have a maximum of 10% left.
That's right. So
So
that's
we would
good.
have that, Frank.
That's good.
It's below.
Yes, but
No, that's
the
good, I like
voltage
that.
does not
We take the
indicate.
residual out, but then we credit what we added to charge.
Okay, there we go.
Because if we'd taken all three did that, we would've got 3 credits. for
That's
each.
right, but you have to add whatever's left in that battery.
That's right. That's
Because
correct.
that's the total power of the system then.
That's what we had put out that would be drawn out. That's a credit to us, and that's good. That's fine.
47, I think you're gonna.
I believe that's gonna do it.
Sure, we got, we are at 70
We've
million.
got to show Frank that this thing will do that, see?
Yeah.
Well, this, I'm gonna tell you right now, you're at 1 hour, 39 seconds. 1 hour, 39.
Minutes, and we
Yeah.
come-
It'll come out to 140. It should have died at 1 hour, 6 minutes.
See, even with the 152, that residual that's now accumulated in that new battery takes us over the hump. So we're
Take
getting
you way over the hump.
So we're gonna be there. But that's
If it
good.
dies,
I'm
it
really
doesn't look
glad-
like it's gonna die.
No, it slows it down because
Really glad you did that.
Take a look at all those batteries.
That's good.
Yeah, they're under the
Oh,
table.
Yeah, let's see.
active.
That reminds me of that time, I was sitting in that conference, Tom, and they were all going, shit, he must have dug up the floor in the middle of the night.
Well, I like it.
51, 53, 54, 55, 56, I got this calculated, Tom, right down to the nap.
It's gonna make,
40 minutes.
with our residual, we're past that 152,
Are you both draining and
so. With it.
Oh, yeah, you know what Frank is, we drain them.
Uh-huh.
But see, there's a residual charge left in the
Yeah.
battery when you drain it like that, and that's what Frank's taken into account.
Yeah.
But he also put the battery in for charging here again.
Right.
So we get credit for what's in this battery now, that we just charged partially.
Yes.
When it runs out.
Anything
we have
over
some credit.
10%.
So we have enough looking at us right now, I'm pretty sure, to say we're there, right now.
Mhm.
Frank was looking at 152, but when he adds a residual in this
It's
battery,
way over.
we're back down to, no more than 140.
Mhm.
You're already past that.
Yeah, and the longer this goes, right, Frank?
But let it run, the longer it runs, the better and the more confident we are. So the higher that number turns out, the better we are. In other words, it's all gravy from here on in.
It's doing its little thing there, Tom, you know, it's got a few, maybe about.
It's running off the primary battery to the
It's-
primary
it's-
battery's
the
exhaust.
Primary battery's exhaust, just about, but it's sustaining, I go there, and it'll quit when it gets to residual.
See, I love it because what we're proving is a fundamental thing. The
Yeah.
batteries are really transducers and so are generators.
Yeah,
And once they make that dipole, the vacuum really does power the circuit.
yeah,
And by breaking up that
it's weird, isn't it, Frank?
that symmetry around that circuit, breaking that circuit into those two halves where they have different responses,
Mhm.
we can violate that thing that normally enforces the Lorentz condition. So we can break the Lorentz condition. Once we can do that, we have an open system, we are free to have overunity. Never unless we got an open system. It's impossible. Until we break the Lorentz condition, it's not possible. But we're proving that we're breaking the Lorentz condition.
Boy, it's still popping that battery up there too.
Have we arrived at how we get the torque that thing had?
Yeah.
Did you figure
Well, we
out?
went through some machinations and short of dynamometer, I think what Frank's doing is better.
Okay, all
What
right,
Frank's gonna do is much
It
better.
would,
all right.
we would all be a little more confident if we had a small dynamometer, knew, you know, the plus or minus number.
Frank's gonna look in Germany when he's over there,
But
and let me know.
since we don't,
They got it.
we're safe siding it by subtracting residuals. so
Okay,
it's kinda-
fine.
So Frank,
Which is
whatever
okay,
comes,
we're still gonna come
something.
out.
By inference, yeah.
I would rather be
I'll buy it.
conservative
Probably
and know that
so
with a
expensive.
dynamometer, we're gonna
It is
beat that
expensive.
number, then go the other way. I
Yeah,
would
I
rather
bet
do
you
the
it's-
conservative
Yeah,
method.
err on the low side.
$400-500.
If we got to err, we err at our own expense.
I can send Frank the money, it's not a problem. I will FedEx him the money.
That's not a, when we get something, then we should get
Well, German chocolate too.
That's not gonna interfere with the report, though, is it?
No,
Getting in this
no,
dynamic.
no. But we need one for the lab anyway.
Right, okay.
We're going to the next phase of where we want to really start cranking here.
Well, nobody get shaky here. We're sitting on the gravy train right now, so we're gonna sit here till that thing stops. We ain't gonna move.
Yeah, we're in a slide condition right now.
This is the good part from now on.
This is kind of.
All the rest of it was just to get to here.
That's a lot of work.
Yeah, all
get
the
here.
rest of it was just to get where we are right now while we're watching it.
Well, we don't know what's in this, what's left, but we'll know in minutes when we connect it, right?
Yeah,
Not until it stops.
And then we can integrate this again, right, Frank?
yes,
But you're gonna take this measurement, right?
yes.
And that would have been multiplied by 3, right? Yeah, because whatever this does in this many hours, it's multiplied by 3. Because you charge 3. So if you
Okay,
take
we're
that,
getting there.
But tell him, Frank, what to do, John.
well, if you take 1 hour and 44 minutes and multiply it by 3, what do you get? What do you get? Do it on your computer. You're over 5 hours.
Yeah, we're over that 4 hours for one
Now,
battery.
subtract.
But see, by allowing residuals out of that, the more we're over, the better. That's what I say, from now on, everything that's going on here is the thing that's actually in the black for us. You can say up to about now, everything's been in the red, but right now we're in the black and the black. So that's where we're at.
Let's see, I've been there, I don't know how many times.
Yeah. But you see, Frank's got to be there when he.
Frank is here.
Frank is the guy.
Frank is watching the thing
Yeah.
do what it's
And
doing.
the instruments have to see it, so that's.
Yeah,
what we
well, the
have to do.
instrument is seeing it,
That's
Tom.
right. And that's good.
It's seeing it good. I like that thing, Frank. You don't sell off your used test equipment, eh, Frank?
Almost constant rate with a little.
45 minutes.
Keep going.
About,
If it runs midnight,
This is
John,
the
I'll sit right here
voltage
and look
left
at
in the
it.
battery.
Well, we don't know what it's gonna do, Tom, because that battery,
Whatever it does.
well, you and I know what the battery is gonna do.
No, I don't, but we'll see. That's what.
Well, that's the whole point of the test, is to find out exactly what's going on.
Geez, if that was a gigantic machine and I was an ant standing there, it would have just popped me for a loop, Frank.
It doesn't want to stay below 850, I know that. Keeps going above it.
yeah, because the current decreases. That's why.
Yeah, it doesn't wanna stay there and it keeps popping back up there.
Well, you guys want to go get a beer?
Hold on.
No.
I'm not going anywhere until that thing stops.
That's a joke.
No, we're not done with that.
No.
No, but I mean, we had tried to be stopping point till that
Frank
morning.
says champagne, I love it.
Yeah, you're gonna pay. Tom's gonna buy it.
I will, too.
Did you get enough pictures?
I'm getting more.
Okay.
I didn't Yeah, getting them as we go along. I got 2 rolls, so.
Oh, great.
What'd you do?
Just about out of tape.
Hey, you're gonna save some, right?
Yeah. At
Okay.
least 30 minutes. I could save an hour if you'd like.
Okay.
Okay, we're in the middle of a tape.
No. The only thing we could determine is what is the residual
Yeah.
voltage and what is the residual
Well,
charge
this
in
is-
that one. But
Right.
it would
Then
be,
what, minus here, right?
yeah.
Minus here. You want minus here, right? You want plus here, and plus here, right? So this battery goes over here. So Frank, I'll let you connect this up so you know what you want to do. I think this is the way it goes, right, Frank? This green goes to the plus here.
We're going to put
Monitor.
in parallel
Power, right?
voltage.
Yeah.
Voltage now.
And this is the current, right?
Yes.
Right?
Let's see, plus coming
Yeah.
from here,
Minus.
going to plus here, yes. Okay, that's correct.
That's good, Tom. And that's not taken into account the work.
No,
So how long did it actually run?
Well, we'll get all that as soon as this is exhausted.
1 hour, 48 minutes.
Thank you.
Yeah. It's kind of, you keep doing it long enough, Frank, and we'll figure it out, right?
Yeah.
Well, you had it too, boy, it really did it, Tom. Calculated it right out.
That's good. That's good.
You know what's phenomenal? It's like there's a lock on that battery. I mean, dead lock. But you can explain that, Tom.
Well, if I work a little bit, probably enough.
Yeah.
No, we do have an explanation of how we're getting the energy out of it and how we're getting it in there. And, fortunately, just energy flow into something doesn't cost you anything.
Right.
If it did, we have no use. But if you can get an extra energy flow input, then you can have overunity system. You can have open system then not in equilibrium. And that's a requirement.
Now we have to run this one out, Tom.
And that doesn't matter where you got a home heating pump or where you got an electrical system or what, that's the
Or
requirement.
you gotta count what's left in this one too, Frank.
Yes,
So you gotta run this one out, charge
Yes.
that one,
yes,
and then put this one back over here?
we could, yes. Then we
Get more time?
we have multiple data, yes.
Okay.
Then
So
the
under dinner.
residual voltage really
It's your steak, Frank.
is eliminated or is no longer a factor. Okay, let me just select here the. What was I going to do?
I don't know, Tom. Well, I know, but I can't determine that. I don't know how long this is gonna go.
So we have
You sound like Jay.
No, but I don't wanna, I'm not sounding like Jay, I'm trying to, he's calling, you want to know what time?
Oh, so what the test is, but
so probably latest 7 o'clock.
We'll be here till 7.
No.
Oh, no.
We will be here until 6:15 maybe.
Okay,
yeah,
all right, then
Yeah.
7 is okay.
yeah.
7
Good.
is perfect. Yes.
Okay.
That's pretty good. I like this machine.
We have better ones, but I'm not too familiar with all of them.
You go more sophistication than that? You go to dynamometers that you actually put vehicles onto?
No, we have electronic brakes where
Oh.
we determine the running overload test of motors,
Oh.
how they behave temperature-wise,
Oh,
to see if they can be potentially a safety hazard or a fire hazard. And so on, we have a couple of laser measurements, ergonomics measurements, and so on. So yes. Do the last. That's what's left.
you know what? First battery ran 3 hours and 18 minutes. Right?
313.
At 3:13. So, if you took, that would be 4 hours and 42 minutes.
See, a silly way to look at it for a real quick estimate
Minus,
is we got the residual
Yeah.
and his battery was
Yeah.
charged.
yeah,
So you keep credit for the whole battery, see, whatever it
yeah.
ran, 3
Right.
times, so we're there.
Right, so you got a machine. Well, you can't count the mechanical work, so, but you can assume that it did so much work.
Yeah, it's coming out. This is showing.
Yeah, because,
This is showing
I
what
see
it,
what Frank's doing now. Yeah, it makes sense.
yeah. As long as you do something that does work,
Yeah.
say actual work, then you're doing measurement. And if we got some charge or something in the battery, then what we gotta do is do work with it. And really positively say, well, whatever's in there, you can get this much work out of it. really, work measurement is what we have to do.
It comes out about what I said, Tom.
Pretty close,
Yep.
pretty close.
We actually, are we ready, Frank?
Get it.
You had to use the book
I
last time.
cannot repeat what I did.
Yeah, whatever's left in here, whatever's left in this battery, Tom, in time, has to be added. Then this one, whatever it charges this one to.
He's got the numbers for how
Yeah.
they add it, so it'll work out. He's got them rolled in there.
It's kind of phenomenal, Frank, the contacts, make contact.
We still have one measurement, I guess, on this, battery one.
This one here.
Yeah, okay, you've already changed it, yeah. we
Yeah.
still have it.
So. Notes.
Okay.
So,
See, what Frank is doing, he's saying, we have these three batteries that we charge, and essentially they're identically charged, plus
Yeah.
one little bit variation for statistics, but basically essentially the same
Yeah.
charge, same battery, same thing. If we cycle one, through all the cycles we can get from it, to find out
You
how
get the
much
whole
energy we could keep, then we multiply that by 3, and once we subtracted whatever residual had to be on the front end, we're there. He
Yeah,
has it, and that's coming out, that's gonna come out with this next measurement. We're there. I think so, unless I missed something really.
no, it's
We're back at the square one.
If you take the total time that the primary battery ran, right?
Yeah, what he's doing is saying, anything you could do with one of those batteries that you could charge, whatever set of cycles you can run from then on, accumulating a little more each time, when you run that string out, you could do it for all three.
Yeah.
See, that's what he's doing. He's determining what you can do for one string, and you're saying, well, you had 3 strings, so just multiply whatever that turns out to be by 3, and then take a look at that number. He knows exactly what we put in, took out of that battery we had to pay for.
Right.
So he's got that measured very accurately. So when the strings are determined, then we know where we're at, because that's workout.
Well, I see you're, in other words, instead of taking the work from the motor, you're
He's leaving
taking
the
out
same, he's leaving the same standard of work.
in electrical
For
energy.
the whole string, so he's running that string out of there and measuring it and everything. So that when we get through, we have the measurements for one string. And he'll take out whatever residual had to come out or whatever on the front end of that. When he gets through, he has what one string did. And you multiply that by 3. The 3 strings then gave you this, and you know what you put in
Right.
on that one to get those 3 strings. That's what he's doing.
You have to reset first. You have to do it 3 times and then it does it.
okay. Then 2, 3 modes. Inputs. No. Time of 1 hour. We don't want a balanced mode, we don't want the harmonic mode, we don't need the waveform change, we don't want to have a bar chart. On the display, we want to have hours, actually here.
Yeah.
This RMS.
I got it. I gotta get a book from my library, just because of all this. I want you to recommend a book on physics. You may say, well, I don't want to write what would you recommend as our, or just have in my cat library?
I would take a good sophomore book, and I've got to give it up. I have to think of the fellow.
There's a key out.
A good sophomore physics book, see, they have to cover
We
all
are back
these
in
areas.
business, good.
Are we ready?
Now, there's the whole.
You tell me what.
Yes.
Go.
Go.
So I would suggest that.
So, sir, do we have everything
Depleted.
fine on the
It's called.
primary side?
College
Yes.
physics or.
It's just asking for certain. Go look up. Get it for you.
Okay, Tom, she's running.
Very good.
Yeah, down the previous week.
We can do that. See what it's in place here.
So this is integrated again, right, Frank?
Yes, integrating. Micro FLOS, okay?
Yeah. Because the currents are small, right?
Yes.
You know what, maybe he's right. Maybe there had to be no current, right?
Yeah, could be that is very short. We only see the electronic,
Yeah.
the current of the electrons.
Yeah,
We don't see the ion current.
right. You never see it though, right? We only assume that's there.
Right. So, let's see.
We only assume that's in the battery. We don't even know if it's there. Back to 120 mils ago.
Very well illustrated.
There you go, forever.
We have the time now. Roughly.
What's this man?
Certainly.
Let's break chest, Frank.
That's what the engineers are for. If you're going out.
It's back to its normal thing, 120. From a partially charged 20.
Right. It still has 11
7.
Yeah, well,
But what we need now is the time of this one,
yes,
right?
which this instrument will give us.
And then you need the time of that one.
Okay, that's a good one.
And that gives you the 3.
Yeah.
The 3 curves, right?
That's three now.
So it would just tell us again how much we
Put back.
have gained, put back, and then always goes back to the residual voltage. I would like to get a handle on the residual voltage, how much, or into charge, how much is left after the
Okay.
motor stops.
Okay, I see
Or
what you're saying.
eliminate that and saying, okay, this is what we gain.
Good.
because that's an unknown for us. I don't like unknowns.
See this, Frank? See, look what it does. You watch how this does it. Yeah, pops it out.
Yeah. Yes. it's trying to recover, of course.
And
but
then
in
this thing's
addition-
smacking it,
yeah,
right?
In addition, it's getting.
So what he's
the
right
bootstrap.
there, what's happening is the electrons are piling up
Yeah.
on the ion, and then ion moves.
Yes, once you have.
And then you get a charge.
Once you have the potential,
Yeah,
or the potential difference.
well, you can
then-
see it here. See how it popped it up?
Yeah.
Jesus has popped it up again. Right. Right. This could really, the effect, once the effect's known,
Yeah.
exactly how to do it.
Yes.
Y'all suddenly find out you plug something in the wall and don't have to have no permit,
Yeah.
which we all looked for before because every car running around town's got 100 amp alternator. Now why's it got the 100 amps? Doesn't make sense anymore, does it? Well, it does in a way.
No,
Because-
you are running all possible electrical sources on your.
Well, you know how I looked at it differently. I always looked at it differently. And that my way of always explaining this to somebody was if I took three, I'll do it, right? I can do it over here. I took these three batteries, right? And said to you, this is what I have. Now, how can I keep all three batteries charged? Well, see, the potential is this way. If you put the two negative terminals together, right? And then measure the two positive terminals, one of these will be a negative. And one will be a positive at a higher potential. It's the same thing that's happening here with a cap. So now, the solution is to go like this, right? It's like a guy with a, and you want to know what? A guy one time in Germany said to me that when they, during World War II, they didn't have any money for these zinc carbon batteries, so they kept rubbing their keys across it, and they charged them. Now, what charged them?
Mechanical energy.
Yeah, brush contact charging. Same thing that's happening.
So when I'm cleaning my terminals and my battery, I'm actually charging my battery.
Well, not necessarily. We're talking about a specific thing that this guy did with his key. The way,
What about the batteries they had in the aircraft?
oh, let me tell you something.
Where you turn the
This-
crank?
This is not, no, listen to me. This is not known. Adolf Hitler, in his German submarine fleet, had mercury cells. They went around, they got all the mercury. Do you realize that mercury cells, what the potential of a mercury cell is?
No.
If you could keep it from oxidizing itself? And so they developed in these U-boats, right? What it was a copper disc. And when the battery started to run out, you just turn the disc and scrape it like that, and then the battery was back. Guess what? The Americans dumped them out in the middle of the Pacific Ocean because they didn't want anybody to know. You gotta remember, Germany had to use...
They had great inventions, man. Are you
Yeah.
kidding me?
They,
Unbelievable.
no, listen, they didn't have anything.
Technology was great.
Are you kidding? They were able to run these things.
Well, during
They
World War II, U.S. and,
You
I mean,
just
those,
type in Dan's Coal.
they
were pumping out a lot of
developed
stuff.
more technology in such a short period of time than
Type in Dan's
ever.
Coal. Captain.
We talk about radars being developed, guidance
Well,
systems.
you'll find out something with magnets and wires, what they have. I think this happens every,
What test are we on now, guys?
well, Frank will tell you what's left.
Okay, good.
So, we ran down this battery,
Okay,
but charged this one.
okay,
So now we are using this charged battery again to run the primary
Okay,
and
good,
charge
good,
against the
good.
secondary.
We're getting to the time here,
Good.
which we're already 10 minutes and 15 seconds, right?
Yeah.
good. Excellent, excellent.
And what's going in?
What do you mean, what's going on? This is
Something
reading
special Frank
the
brought.
time and the hours in microamps, right?
Yes.
And see, we're not using any current to charge the battery. No weird. Look where this one is, right? Come
Still
on, look at
sitting
this
there?
one.
Something's charging.
Well, that's what Frank is gonna determine when he does his
The
thing.
potential
Yeah.
we are generating.
Well, I'm gonna get so far.
So technically,
I just need it, you know?
Tom,
Yeah. Oh.
look where the other dead battery is now.
I'm sorry.
Over here.
Very good.
So Frank, you can run that one after that one.
Well, we stay here till it goes down.
You mean until they don't run no more?
This is the great.
You're gonna be here a while, you're gonna be here a while because this is
That's all
at
right.
11.
I got nothing better to do.
Who's gonna be really unhappy is Tom Walsh, he's so worried about eating.
I'm not worried about it.
The way life is.
Well, we have to kill off Frank.
I only have a piece of
Frank
time.
I know, we have to take care of Frank because we really made him work.
Frank, you need another pad, let me know. When you run out there. I think I have another one.
See the damnedest thing in the world. See you humming away, Tom. Well, that's my estimate here.
Well, I like the string approach. The string approach gives you credit for your process by that.
Right.
So that's good. That's a good approach to it. It's a
The
very-
process is what's very important about this.
That's right. That gives you credit.
And
for
how
your
you
process.
get it out of the process.
That's correct.
And we see that with the scope.
I'm sorry?
John, get in the middle of these two guys, I just wanna get a picture of you.
Okay. Here, you guys just say he was a midget. Yeah.
John, the big, you are a midget.
Wait, I just one, that's just warming up.
Oh, come on.
How come they're both taller than you?
I don't know.
You want me to get in the middle and make John look tall? Okay, light up, here we go, good one.
It all goes in a book. Did you ever see the book? Tom?
Yeah, I should.
Yeah, he showed me. Well, yeah. Very good.
For the archives.
The book of good times.
You know where the book goes, son.
The fun book. I call it the fun
Sitting
book.
right here.
Okay, let me get,
You know, I took 3 times as many pictures as are in that book, but, you know, a lot of them are duplicated, so I still have a whole bunch of pictures, but they'll just go into the envelope in the archives. Into the book.
Yes, everything you was screaming about is absolutely true, isn't it, Don? It's how you push it there.
Well, the strange thing is, in spite of all the theory that everybody teaches in all the universities, the vacuum has powered every electromagnetic circuit since the beginning, still does. Battery generators do not power circuits, I'm sorry, they don't put one watt on them. They make the dipole.
Yeah, they split the
You
charge.
gotta go to particle physics to find out what the dipole does, which we didn't discover till about 40-some years ago.
Gentlemen, I'm
And
changing
they had to put it
tapes.
into electrodynamics. Might be the old man.
Oh, my ass.
I could do a lot better, John. That's years and years and years ago.
You get one electron pop on that motor, you can see it when the spike goes like this.
You'll
Boom.
see a fuel cell.
Everything else is potential.
Nitrogen.
So you throw little electrons in there every once in a while, John, and you move the zero mass.
Advantage is that the electrons are not used, it doesn't need charge. Just
See, what we do, what John does is he stops those electron
Right.
currents at that interface on that plate before the ions start moving. They're so heavy, they wait a while before they move. And during that moment, you pile up the electrons, you get a lot higher potential. As the current density, as the charge density goes up, that's the definition of potential. You get a higher potential. The potential goes both ways. It over-potentializes the electrons, gets more energy on them, and it over-potentializes the ions. So it gets more energy collected on those ions when they do move to recharge it back. So that extra potential that you get essentially for free is what is
That's
really
good, that's the damnedest thing. This,
See, that breaks the Lorentz condition. That breaks that Lorentz
see,
condition.
when you see that wave,
Now, when you have electrons going all the way, you
when
don't
you see
have
that back there in that spike,
That goes
shrink,
fast on the other side of the way here.
that's current
So
being
you
pumped by the
can't do it no
motor.
matter what you do in a
In
normal
the current.
circuit unless you do
Right.
something to break
That's a few electrons.
current loop.
Everything else is massless after that,
Yeah.
running down that wire. See, you must. I've been trying to tell this. Well, Tom will tell you till I was blue in the face. When you see that spike on the scope raise itself and then shrink, that's a few electrons that the motor adds to the rectifier and the cap. After that, it's a massless charge.
Well, the other thing, and we're just filing it.
So a few electrons go down there,
Yeah.
but the rest is, you can't measure because there's no current there.
There's actually a different way of
Yeah.
charging that
Oh, yeah.
capacitor used also, which is very complicated.
It's almost,
It's not simply being charged with electrons, let me put it that way.
it goes a little bit longer than that.
But it's the basis
It really
of how
has.
this capacitor is being charged is just
Don't
now
you
being
know that,
looked
huh?
at.
That's what's
It's
starting.
an area they know about from Dirac's electric. And they use it in certain places, but they don't use it in normal circuits.
That's nothing you can get.
And now they're beginning to say, in fact, I've got papers now, fairly recent papers, 95, 96, 97, 98, where physicists now turning back to that and said, hey, fellas, we oversimplified this problem. We cannot eliminate this other area. We have to go back and take it in. If we have a field, we have a potential, we have to calculate it. We haven't been doing that. So, you know, they are about to say, come out with a fully rigorous basis for how that thing is being charged. It isn't being charged that way along with electrons at all. As a matter of fact, we're not even having to furnish the electrons, it is charging. So, but, you know, I have now 2 or 3 papers which give a basis for that, where I now can say, okay, this is just an area that, for some reason, nobody worked this problem. And now they've started working it, and yes, there really is some real physics here. So, the good part is to
Partially
pick out
charged
something
battery
that's already
already
shown
over
in
20.
physics, you know, you're not hatching it out of the air.
Yeah.
It's not some wild idea that'll hatch up.
You
And
know,
it gives you a good mechanism, and then if you can find that working in the circuit, you can use that. And that's basically what John's doing. He's been using that all these years. Nobody could explain it because everybody was using the normal circuit theory, which doesn't have that. Now they're saying we left that out. So now all of a sudden we can put it in there and we can explain what he's doing. We haven't been able to do that until, I'd say since 95 or so, the work since then. So that's relatively new work to be able to explain something John's been doing for 20-something years.
Well, I think there's a lot of brilliant men out there exploring this now.
Well, what's
And you know, that's how breakthroughs come through.
What's encouraging
Dedicated
is
people.
some of the physicists are beginning to work in these areas
Yeah.
that got bypassed. If they would turn these young fellows loose in the universities and give them, and let them do that kind of research, you see, they have to go, like a grad student has to go where he's funded to do research.
Sure.
If they would give them a little funding and turn those young grad students loose and those young postdocs, this would be out of here and boy, they turn the world over in 2 years.
Well,
It's ready for the turnover.
yeah, the world needs it.
It does, it definitely needs it right now.
I don't know, that's because we all have computers in our home, and it's hogging all the energy.
Well, the energy demands are going up in every country, even all the developing countries and everything.
Well, they get,
We need to be
I know.
able to
I was
get more energy without having to
read an
burn
article
more coal
in the
and all
newspaper
this.
saying that the dot-coms and the computer revolution increased this demand, when it wasn't there before.
Well, one thing that increases, a lot of things are pretty inefficient. A normal ceiling fan, when you really look at it, it's pretty inefficient. Some of those things are only 10% efficient. They're wasting 90% of the energy in the fan.
Oh, probably, huh?
And a lot of it can be helped just by changing the blades. You can redesign the blades, that's known, in aerodynamics, that those blades are the way they make them cheap. If they spend a little more money on them, they can make them a lot more efficient than what they are.
Yeah.
You can go up 25, 30% with no problem.
I'm just antsy to get going into the refinement stuff. I want to get that project started and going, and then we start working on refinements here.
Well, that's right, but what we're doing right now is critical. What Frank is doing
Well,
is
sure.
very critical. We have to have independent, good measurements. We can say something until we're blue in the face, but scientifically it's not acceptable till somebody else says, and I measured it.
Yep.
It's the observational phase.
That's right.
Well,
It's a good indicator if we say it, but that's all it is, an indication. If Frank says it, I measured it. See, that greatly strengthens the
And I
indication.
repeated the measurements.
And I repeated it or something, or somebody else may say, well, I'm gonna do it, so they come
And
in and
it's
they say,
repeatable because we,
It has to be a repeatable measurement.
mm-hmm.
It cannot be a fluke. Well, this one is repeatable.
Elena? Well, I think that's the point of going over this and over this. You know what I'm saying?
It is a repeatable experiment,
Oh, yeah.
so,
Well, we're gonna repeat.
the little motor will run, the same batteries you can buy
Oh,
off the
sure,
shelf.
sure.
You can do new batteries, you can do the experiment again, it'll work exactly the same way the next time. Somebody else can come in and say, well, I want to do it, it'll work exactly the same way next time.
Yeah.
But it has to be repeatable.
Yeah.
If it's not repeatable, it's not a good experiment.
No, I agree. I agree. I'm just excited about getting into the other one there that's coming along, and,
Oh,
because we're gonna do the same thing over again. You know what I'm saying? And just keep going from there. Till we get the refinement, we start refining that.
9.62.
Well, I like it because everything I've been working on for about 30 years is sitting there on the bench beginning to work.
So John, how long do you think on that other one, before we get this other one?
Discharged?
No, I'm talking about the model he's working on right now.
You day.
Because in,
so we test it tomorrow.
Yeah, you wanna wind the coils tonight, Brad?
Sure.
Frank would too.
Yeah.
He'd love it.
You wanna take some solder off some rolls?
Yeah.
Well, I'm just saying,
Doesn't make any
I want
difference
to
to
get
me,
into
Frank.
refining, man. I want to get into that stage next.
well.
We gotta just
Frank
move along.
expressed it perfectly when he said several times about optimization.
Yeah.
Not only,
Well, it's
you know,
more than
That's the
that.
next stages we want to get into.
Well, isn't timing part of optimization?
Sure.
Coil winding? is
Yes,
part of
all that is. There's a lot of variables.
Right.
The other thing, there are scale-up effects in this area.
Yeah.
So you have to redo your
Yeah,
phenomenology
you have
every
to,
time you
yeah.
scale up. And you have to adjust it. It's the same phenomenology, but the degree is different. So you have to do your phenomenology test again and
Yeah.
optimize for the scale you have.
Right, so I came up with a solution, Tom, that we know what the efficiency of this generator was because we had it tested.
Yeah,
We had a guy methodically pick us apart about this.
yeah.
And when it came out to be 120%, he says, oh, that's not.
They were from MIT,
Yeah,
those guys, when we went through that portion of it.
Tom was standing right there when he says, I've been looking for this my whole entire life.
Yeah.
I'll never forget that quote.
Which is a
That's in the
different
back of my
concept.
mind.
Yeah, but that one was, those were the wrong people.
Yeah, those were the wrong people, Gary.
Well, it was the wrong time too.
And then he says to me, oh, well, you don't have that much. I said, oh, you got a 10 times probe there. And he goes, oh yeah, that's right.
Well,
So unfortunately,
30
our,
minutes, huh?
unfortunately, our discharge test will be
Mariners last night.
a little bit weak because the current is
Yeah. He's looking at.
really, really,
Well, really,
really
huh? Like, is this one?
See, he's doing the measurements. It's the measurements.
Yeah.
You see him throw the fake money too?
Huh?
See him throw the fake money?
I think the whole thing.
He got up to bat.
29, 55,
Did you?
Yeah.
The fancy.
7,
Oh, I didn't know that.
Well, you know, maybe
30
a third of
minutes.
them do, but 2/3.
Yeah. They
And
should.
then the media played up the Brewers. I just.
He's a good kid, he's 25.
about 35, 36, almost 40 minutes.
Golfers are jealous of each other though, like in this business. In the baseball business.
You know, what do we do with this one,
Because
Frank?
you're working for a team, I guess, whereas when
Put
you're
it over there?
working for one person.
sure.
You want to count that time too?
Against
Yeah.
everyone else,
Yes.
you're your own team. Maybe that's
I
why.
would like to
you don't present
repeat it as many
favorites.
times as possible.
well, yeah, Frank, I agree with you, sure.
The uncertainty of the residual charge. And
It's not
have
a team.
some
It's not a
data
team.
to,
Like a lot of people don't want to call.
for calculation.
Right, sure.
So, in the time frame of
No, I think why they're,
Okay, so it's going to be
33.
that's one. And what he really did for us last year. He was the same.
Well, it's kind of funny to sit here and realize that in the 1880s,
They do this.
they actually had it in theory at that time. But because they didn't have computers and that forced numerical methods, that was terrible.
But,
Well, didn't they have to do all the calculations in their head?
And so all the rest did was try to simplify the equations where they could be easier. And they said, well, everybody knows potentials are just fictions. They're not even real. So you can change potentials all you want to, as long as you don't change force fields.
Right.
And that's what they did. And nobody at the time at all had the slightest notion
Yeah,
that they were
that's
throwing
what
away a
I'm
whole class
That
of
is kind of
He
incredible.
became way above the school.
This is staying with that
He
law.
became an
That's-
icon where he was the best
Yes.
known athlete in the world.
Last as well.
And no one was trying to figure it out.
no, because when
Never changed, never changed.
Well, Frank, you know, this stuff has been on the internet, Tom will tell you. I've been telling them all these times. You don't got it.
Yeah, but they won't build it like you build it, John.
No, they will never take the time to balance it out, and it's going now, so out of just that little time,
Michael Jordan.
that's how much charge.
If you deal with people who are still open-minded and have enough scientific background, if you deal with people like Bedini and Bearden, they have absolutely no problem in understanding this. In fact, once they see the equations and work through the equations, they have no problem.
Well, the equations don't lie.
And all the rest of them are, quite simply, the rest of those guys don't matter. What matters is, does it measure on the bench? It's got to be there experimental. And the other thing is, do you have a good theory to explain it? Can you explain where the energy's coming from? Or how it gets in there? And the answer is yes. We've got a paper published already in Foundations of Physics explaining that.
dozen other.
So we have a rigorous paper on that. You can get that energy out of that.
Yeah, he did it.
But it's coming real slow, but it's coming.
If you think a great player coach, where you didn't have to play all the time, but you could go in. There's been other player coaches. I'll tell you one thing.
So maybe then,
He'd fill the
how long
stadium.
does it take to charge one of the batteries fully?
18
He was
hours.
sitting on a bench and a coach.
So we can leave it on tonight.
Fill the stadium.
Yeah.
Because he has a charisma.
Yeah,
He's
enough
got
time,
what
yes.
the coaches want.
Whatever protocol you want.
Whatever you want to do.
Let's
I
have
remember
one
the
fully
last-
charged battery
Remember that one against
Okay.
Utah?
running some.
I mean, really
Last
full.
shot, they won by 1 point.
Well,
Six
you
games.
gotta run them to the same amount you had here.
No,
18,
Yeah, they beat Salt Lake.
oh, 4,
It was a 6-1.
6.
And there was 4 seconds left, and Michael got it in and won the game by a point.
Yeah.
Which was, you know.
It's getting a little slower now.
Yeah.
It'll be all that much slower.
no, well, we still got this one.
Yeah, that's right. We should be on a sort of a decaying
Can I-
curve as we're running.
John, can I remove?
Yeah, because we're running a dead battery.
Yeah, that's what we expect to be.
Why is the voltage still 9.5 volts, whereas the other one at 8.5?
Well, it's got a little time to go there, right, it'll kill it. It depends on this battery too. What did you tell me, Frank? Each battery changes a little bit. There you
Okay,
go.
we're getting there, we're getting
Okay.
there, there we are.
Okay,
Okay, hold it. So, we were at
34.44.
and 25, 65, whatever this,
What was the time, 34?
34, 45,
34, 45.
34, 45, so 34.
And that didn't run an hour and 40 minutes because it was not a charged battery?
right.
Is that, okay, that, just clearing it up, I wasn't sure.
Okay, and we had, what was it, 6, 75, 85.
And our battery over there that we're discharging is at 32.1. And the band plate on.
Okay, so now,
Oh, so it's reading some current,
yes,
but
minimum.
you don't know from the waveform actually what part it's integrating.
Well, it's
only-
probably the peak. I seen it
no,
flash.
it's
I
not
seen when
integrating.
I watched it.
It's integrating RMS value, so it makes an RMS value
Okay.
out of the
Oh.
peak. And, but,
What I noticed when it changed, you heard it snap.
yeah,
Okay, so now we take this battery, put it there,
yes.
and run it out.
Oh, let's stop this.
Okay, Frank, I'll disconnect these wires.
The sports commentator
Right.
on
Yes,
NPR
please.
is,
Okay, here's this battery. Primary again.
over 40.
And see what you
Connect
get.
everything here,
Yeah,
as I have,
okay,
to the minus.
there, right? Okay,
Isaiah
and
Tom.
this is plus,
What's plus?
that's plus, and this one goes over here.
Yes.
They cut Isaiah Thomas out.
So we have 10,
When
about
they,
75 watts left
they
here.
first, it was the first year they allowed professionals to be in the Olympics. Then they had Jordan, and all, and Isaiah Thomas was the first, without getting his personnel. And he should have been on. Isn't he now coaching the, is he coaching Detroit?
I don't follow basketball.
I don't think that they should have pros in the Olympics like they do. I think it was much more fun when it was college basketball players and it was college hockey players. I mean, it's kind of taking away the, there's no more amateurs. And it's supposed to be, they started out as an amateur.
So we actually are depleting these 3 batteries.
No, the same 2 batteries, not the 3. We are depleting just the same 2 batteries. We still have the other 2 not used.
So is this battery here completely charged?
No,
No,
No. Okay.
no, this is the
we're gonna
battery.
recharge now.
That one?
So let me just, we are using again primary E. Oh. Secondary 3.
Well, so we haven't even used that battery. We haven't even used that one.
No,
Number 2 we set aside.
primary 1.
I got lost on the battery switching, but he's got it accounted, so.
Well, geez, Frank, we could use that one and put the 3 back over here.
Yeah, but what would that buy us?
Well, we didn't use that one. That was charged, right, from the
Yes.
original 3.
Right. But again, we don't know the residual charge on this one, so we want to go independent from that one
Okay.
as far as possible.
We gonna do this till it won't turn, Tom? We gonna do this till it won't turn?
Whatever Frank wants to do, we're gonna run that string until he's satisfied.
Then we're gonna hold them hostage.
Okay. That's fine.
That's good, Frank. Are you ready?
1, 2, 3.
Get over here.
This one will not.
You gotta shut it off,
No,
Frank.
no.
That's a pisser.
You guys ever listen to Prairie Home Companion? Garrison Keillor. He had a, he has a gift for really stringing things out, a lot of verbiage.
Yeah.
But he told this joke last Saturday. Ladies in the shower, husband's downstairs working in the shop. Go ahead, don't let me interrupt your test. She hears a knock at the door. She knows her husband can't hear it, so she gets out of the shower, wraps a towel around her, and goes to the door. The gentleman at the door she's never seen before. And he's kind of taken back by her and the towel, and he says, I hope you're not offended, but you're the most beautiful thing I've seen in years. And he just kind of gazes at her, and he says, I hope you don't take offense, but if I gave you $300, would you drop your towel? And the lady turns red and says, yeah,
So,
right.
I'm ready.
Okay.
Tell me when.
All right.
Okay. Lock goes. So she thinks about it for a couple seconds, and then she just drops her towel. And the guy gazes at her, and after a couple minutes or a couple seconds, she's starting to pull up her towel, and he says, wait, if I give you another $100, would you just turn a 360 for me? She figured, well, I've come this far, so she does a 360 for him, and picks up her towel, and he hands her 4 crisp $100 bills. He leaves, she goes back, gets in the shower, finishes up, and her husband comes up later and says, hey, did somebody come to the door while I was downstairs? She says, as a matter of fact, somebody did. A guy I've never seen before, but he drove a big white Cadillac. And he said, oh, that's my cousin. He said he was going to come over. He owes me $400.
She goes into resonance again.
There we go.
He owes me $400. Sounds like something my cousin would do.
What, Tom?
Yeah, in all my days of listening to that show, he's never said anything that risque, and it was just really funny. Caught me off guard.
You use the right machine. You charge a bank of that.
Yes.
They keep switching primary batteries.
Yep.
Independent from the secondaries that you use. Your power problem down in California is solved, Frank.
Yeah.
Well, we hope
So,
so. It's a long
Can
way
you
from
give
this.
me-
Hey guys, there's a lot of work.
give me a couple of those size.
But I can already see the size of the thing has to be. Dodger Stadium. And all the seats are batteries.
A lot of work, guys, yeah. Got a lot more work to do. So, when are you going to Germany, Frank? When are you leaving? And when are you going to be back then?
I'm leaving May 16th. And I'm supposed to be back May 31st.
Okay, so you'll be available after that time sometime.
Yes.
Because I know, now when we get to this next one we want to mess with, this one will pretty much be behind us. We'll be getting into the next phase. And we want to start then to try to start refining some stuff and getting into that and do more testing.
On
You
bigger
want-
ones?
Yes, Frank,
Yeah.
absolutely. Oh, absolutely. That's the whole key here. That's where we're trying to go.
Power.
Yeah.
Yes, you got it.
Power where we have real friction and things like that.
Yes, absolutely.
Yeah.
So,
I mean, at the point, Frank, we can get it up big enough to do enough, and we send it down for full lab analysis. Once we're satisfied up here,
yeah.
we're doing what we need to be doing here. That's the whole point of this. And you can see it does take a lot of work. It takes a lot of people thinking about it, and, I mean, but it's just a necessary step you have to do. You just have to do it.
Well, how many people would do this, Tom?
Well, there are people that try to do
No,
things.
no, they're not.
Well, all right, maybe there's
Well,
not,
the
John,
problem
but,
we have, John, is in the past, we've had a lot of people who have tried to use things like this, fake stuff,
yes,
Right.
yeah, I agree.
to cheat people out of money.
Sure.
Yeah, but that's
We
not
didn't
good.
have what I would say proper scientific work being done on it. So the difference is, we do
You
today.
need the proper scientific work
And
done.
so, to do that, you gotta follow scientific method.
Absolutely.
In other words, it has to be replicable, the experiment has to be replicated, and the measurement has to be independent. Otherwise,
Yeah.
you know,
No.
it's the guy selling stock again, or,
Yeah,
or, you
yeah.
know, Dennis Lee or something.
Bringing that one at a rate which
But if you put it to the hard
Of
measurements,
course, a little
and
bit
it's a
uncertain,
replicable
but-
experiment,
Yeah,
that's
well,
good.
it would be nice to have a constant power.
Yeah. Well,
A
we don't
constant
have it.
current.
Yeah.
So
Well, what will give you the constant current, Frank? What will give you the constant?
special
an
unit.
electronic load.
But see, we still have not put this into the system. This is extra.
Yeah, all right, I understand that. I'm just trying to figure out what Frank's saying here about a constant
This
load.
battery, so far, we've been just using these two.
Yeah, that's
So-
he's running the string.
We are doing
But we
two
could
things
take
in
that one.
parallel.
No, he's just running one string.
First of all, we are
Okay, all right.
trying to
Same thing.
recycle, or we are
He's running-
recycling
Okay,
the
all right,
batteries
fine.
here.
Run down, and you can't
And
do that.
in parallel, I'm discharging one of them, which we previously charged.
Okay.
Just to get a feeling for.
Now, what is a constant load, Frank?
It's an electronic load which gives you a constant current.
Okay,
So
a resistor won't do that?
A
You gotta show me
constant
that.
current of flow.
Oh,
The resistor
all
is
right.
voltage dependent.
That's what you expected.
So the current changes with the voltage draining.
Now, is that constant load thing like a computer or something that you
No,
plug
it's
into?
It's just like
Like one of these scopes or something?
something similar to an audio amplifier
That right there is exactly what's
in
in
the
that book.
power amplifier.
Oh, I see what you're saying, okay. Frank.
So
Well,
you
it
are
doesn't-
driving a
Couldn't you run it
constant
into a
current.
transformer?
There's no transformer
Yeah.
with it, no.
I
You
mean,
might
you're
have-
running-
Well, I'm asking, I don't know, so.
They
You
are.
haven't even touched that one.
We use them for loading, for instance, power supplies
Okay,
to their maximum.
okay,
We
all
are
right.
using them for, yeah.
All right, that gives me a better understanding. Are you gonna account for the variable because of the resistor?
Yes, but the voltage drops, so, or the current drops with dropping voltage, so I can't really tell
It's hard to tell.
One of these days, you'll see if it'll still do
what
that.
our
It does do that.
rate of discharge is, because each of the
It'll do
batteries.
that, keep running by every hour.
Gentlemen, the residual charge.
Yeah. So anything we got in minutes of time is
We
right.
get independent from it.
You know, that's the paper I tried to send you, Frank. I don't know,
He got it, Frank got it.
well, I don't know if he got that on his own, because I tried to send that to him, I know. Was that,
I think you gave me
I gave you the address,
the
address, yeah.
web address, yes.
Good,
I was able to download it. Yeah, on one paper.
Right. that's good.
It's gonna make 11 minutes, just like the one I had.
All blanks.
Yeah, I'll do the same thing.
Sometimes if you email, there's all the
Already at 10.
like this one here.
The email attachment is.
So you're eliminating all the charge
Science
now.
and email attachment.
So it
You're
gives
running them
more
all.
blank field.
Oh,
Yeah, well, I ain't running it off over
Everything
here.
which is normally typed is fine, but everything which is
those are-
graphics
it's graphics.
is not coming through. It clips it
Well,
when it
if I calculate all
This was
out,
an
sends as an
interesting article.
attachment. Yes.
I
minus
never heard of
20.
him before, but it came across,
I'm up there.
We'll have to deal with his calculations, but that's essentially what it's going to be. Thing is, he's running one string down, he's taking out residual, running that string down. When you get through with a conservative estimate of one string, if you did it twice more, you'd have the same result with the other two battery strings. So what he's doing is establishing one string for all three. just
Right.
multiply by three. But being conservative, because you want to be conservative when you don't have the adjustable load he's talking about, where you can have exactly the same power drawn from it all the time. Then it's a simple test.
Right back up where that one was when we started.
Yeah.
In fact, it's over. The other one was around on 4.
whose timing is, are you timing it?
Yeah, Frank, it's time. It's time right here on this machine.
That machine needs a light.
It gave you no amp hours this time.
It doesn't?
Nope. It gave you time that it's running.
Yeah, but no, it's not accumulating, which is anyhow above a 3, I would say.
Well, yeah,
Well, yeah, you can't accumulate a spike, right? Not
You
accurate.
can, but it's dependent on the integrator. of
Yeah.
the, capabilities of the integrator.
But I've been noticing now where this battery was when we started.
Yeah,
This one, this battery over here, see, has already beat that one in voltage. You follow me? This is that thing you're talking about, that each battery is different.
yeah, but voltage is not an indicator necessarily, because we don't know
Okay.
the charge. So only the charge is our indicator. Definitely each battery has
That's what I've been
especially,
noticing.
especially if you are putting multiple cells together.
Mhm.
Small.
Yeah, because one goes lower, one goes higher, and then finally when the two reach the high point, then it transfers to there. But it's a good test,
I
Frank.
really do need those two things.
This machine works. It makes a charge in the battery.
It does. Oh,
Must
we see it.
Yeah,
Runs.
yeah.
And that's what we are.
What do you
Yeah,
have
but
to
you
do
don't do the same thing again here.
You want to draw the
That's what
same
we can
power.
count, yes.
You have to increase the current, though, which means you
So,
have to lower the resistance.
what
You
we
gotta
could
continually
do
adjust it
now-
to let power stay steady.
Yes.
That's what he wants, is a
Charge
steady power.
one of the
So
batteries.
furnish,
Yeah.
then all you gotta do to get the joules is
Until
multiply the
tomorrow,
power.
and then-
Well, it would be that one if you
Then you
did.
can start
Right?
almost anywhere in that test, you see. If you
Exactly.
go full length of
It's
the building,
going to be our battery. which
It's
is
got a
here.
nice.
And then you will put the same
Easy
3.
converting figures and very accurate.
No, just one. Let's do it with one. Let's see what happens.
But I hadn't thought of using that, but it's.
14 minutes.
Once you say, well, of course.
Yeah.
That makes perfect sense. Greatly simple.
Let's see what happens if we just put one.
Okay, whatever. I mean, as far as I know, one primary did all this.
Yeah.
Did all these 3.
They still had quite some residual charge, so
Okay, but you're eliminating that now.
yes, with these 2 batteries, independent from the other 3 which we had initially charged. So, each of them behaves differently. Now we are at 8.7 volts and the motor still is running. Last time at 9.5 volts.
Yeah, because it's a battery. Behaves a little bit differently. You know what I think happens to these batteries, friends? I think that one cell will open up.
Yeah, would be. So one of those three is always a little
Lower
bit-
than the
a
other.
little bit weaker, and it could be on one side or the other side.
Yeah, on
Or
the
it could be
center.
the middle one.
So that
So
means-
that clearly tells us that voltage is no indication for the amount of charge the battery has.
Right.
Voltage is just showing if they are equally charged.
Right. Doesn't say whether or not you charge your battery all night in your car and you go turn the key and it goes click because one cell's dead.
Yeah, yes,
See, it doesn't tell you that at all.
no,
But I'm gonna tell you the big mistake they make when they put a voltmeter in the car.
yeah, yes. It doesn't tell you anything.
Looks good though,
Yeah.
What's telling you is the work that it's doing. That charge had to be there.
So, running now 16.5 minutes, and the primary voltage is down to 8.6 volts, and it's still running at, guess how many RPM?
Oh, that's about 400, 500. Remember, Frank, the slower it goes, the higher the charge.
Yeah, because the phase is
Yeah.
longer. But again, this depends on the capacitor. So if you find the optimum between
Yeah.
your
At the optimum speed.
your capacitor, so on, you have the highest amount of charge.
Depending on the RPM, too. See the speed, the time,
Yeah,
and the capacitance.
right. The function of the capacitor. So on.
You know what, it does indicate that, Tom. It indicates that each battery cell is just a little bit different from the next battery
Yeah,
cell.
there's a little different.
There is a variable in them anyway,
Oh,
isn't there?
you take that into account by getting an average type of thing.
Yeah.
And there is some variation, yeah, but.
Aren't they
on the average,
manufactured
it's a
under
good
strict
number.
standards though?
Yeah, the standard should be a good average for that battery.
I like the way it slows down and pops this thing up harsh. Just pops it up. It does exactly what you said it would have done.
It's okay. The thing is, it has to be measured independently.
Oh, absolutely.
from what you say.
Yeah.
And so, what you need is somebody who's gonna measure it, but at least be friendly about it. You know, watch the instrument.
Yeah, and that can't be measured by us because we don't count.
Well, we have to do the work on the front end, but the
Yeah.
Right,
scientific
absolutely.
community, you know, quite reasonably insists on two things, replication. It must be replicable. In other words, it can't just work one time.
No, you've got to be able to produce it.
It has to be producible and replicable.
Well, that's
The other
producible.
thing is, the measurement has to be
But
substantiated.
that,
independently.
unfortunately, that's not where we're going, but that's
I know.
okay. The theory
No, I
is
mean,
there.
if you took that apart the way it is, and you built that exactly like it is,
It's got to perform the same.
it would do the same thing.
Do the same thing. It is
Sure.
replicable.
You use the same transistor, Frank, you use the same capacitor, right?
You have to.
You use the same switch where it is, you use the same contact, you use the same diameters, you make the same wheel, you put the same belt on it.
Same
The
fan.
same bearings, the same fan, it will do identically what this does.
It'll do it.
Now,
Every time we put it-
why that doesn't happen on the internet's beyond me.
Well, John, first place, those guys won't listen to anything. They are not scientists.
No, I
They're
think they're all,
technicians at best, but
yeah,
not
no,
even
no,
good
they're not in the
technicians. You know,
scientific
they're
field.
not- They're not,
And independent from that, they are looking for usability.
Yes, you're right. That's
So
right. Use a
economic,
Tom has a
economic
good
value.
word for him, Frank.
So we are down now to 7.9 volts, which is kind of surprising. The motor is still running.
Well, it's doing what it's supposed to do, Frank. That's exactly what you would
7.7.
suspect it to do.
Still maintaining.
It's doing its other thing now, Tom.
It's
60.
doing the other thing it is, yes.
Yes,
If it weren't doing that, we would be surprised.
yeah. We know that it's gonna do this, right?
7.5 volts.
Yeah, it's gonna quit. At, well, how many minutes?
So it's
At 28.37. Isn't it?
so it's going to stop
Getting
pretty
close
soon.
now.
Oh, yeah, it's, you can see it slowing down now.
Oh, it's 20. Okay, that's right. That's what I would suspect it to do. I said it would only run 11 minutes. That's it.
Almost
Getting
there.
there, it's all-
Frank's gotta hit that button again.
One big kick here, Frank. One more time. That's
The
it.
current
Here,
slows down.
you want to stop this?
21 minutes.
21 minutes.
Okay, now I can disconnect this battery, right, Frank?
Yes.
And now we find the difference between these two cells. Okay. Okay, that's yours. I'll let you do that one.
Yeah.
Have to run the string.
It's doing the other thing, Tom.
Yeah, that's fine, we have to run the string.
Oh, yeah.
That's good.
And that scope is measuring your actual voltage over there, which is meaningless in the car.
No. So. Again. Set it here.
It's like it's locked solid where you put it.
Yeah.
Let it move a bit, Tom. It doesn't go up, it doesn't go down.
The battery that you did charge? Is that what you're talking about?
Yeah. No, Gary and I run this test until you couldn't run it no
Yeah.
more. We know exactly what it does.
Well, another way to run the test is to start just like we did today. One battery powering, 3 batteries charging. But every time you put another battery on the power, put 3 fresh batteries on and
Yeah,
charge.
yeah.
Yeah.
We get started.
That's another way.
Whenever you want.
You'll get even
Yeah.
better results then. Well, see, it's about as capable of charging 3 batteries as it is 1.
It's capable of charging 4 batteries.
Yeah, but stay within 3 to be
Yeah.
careful. And it's about as capable of charging all 3 about as fast as it can charge 1.
Right, okay.
It's not a thing that, varies by the number of batteries except where it falls off the cliff.
You know, this battery's a lot lower.
Yeah, we're running the string down.
Yeah.
No, it's gonna come back up. You wanna run it right to 0, right, huh?
Oh, yeah.
When Frank is satisfied that he has enough for the end of the string, that's where it quits. So he has to finish one string out, and then he said, well, the other 2 were.
Sure, absolutely.
But you gotta finish one,
Yeah.
where he's got essentially everything you're gonna get out of the string, within reason.
Just gonna turn this a little bit so we can capture some of the numbers.
You do whatever needs to be done from the director point of view.
Okay, thank you. We need to shoot this in Hawaii.
Okay.
John gets the other one going. Frank gets, he'll be back from Germany, May, so probably maybe June. We'll be ready to get going here
That's good.
on starting to really seriously look at it, test it, start making improvements.
Get a little more power.
Well, yeah, I mean, we gotta get to a certain point here.
But there's nothing wrong with this. This is, you've got to have proof of principle experiment first.
Oh, absolutely.
And it has to meet those criteria, independent and replicable. Must be replicable, must be independent and measurable.
Well, I like that other, he's got some real mass on that other one, man, and
What?
on the G-field.
You need the mass on the G field
Oh,
to keep it from
yeah.
cogging.
I love it.
Didn't I say that in that little book, Tom?
Exciting.
That little, simple 8th grade book. The one Watson built that.
Most of those people on the internet don't know the difference between power and energy and work. They honestly don't know the difference. They use the same word indiscriminately.
But aren't they out there just reading to read?
No, no, they're not. They're reading to send you a question so that you drive yourself crazy trying to answer them.
It's a useless exercise. But
Yeah.
Number one, if you give them a reference that's rigid, that's rigorous, they won't go read the reference. And if you give them an explanation, some things are not simple. For example, the vacuum is not simple. Vacuum interaction. If they ask you a question on that and you give them a rigorous answer, but it's not simple, then they come back and tell you that they know it's wrong because it's got to be simple. What can you say?
Nothing.
Nothing you can say to that.
Nothing.
And they absolutely do not know the difference between efficiency and coefficient of performance. They also never heard that there's such a subject as thermodynamics of systems that are open and far from equilibrium. All they ever heard of was classical thermal in equilibrium. And you can't have an overunity machine in that thermal, you lost before you start. As long as you're in equilibrium, forget it, you're wasting your time. So, but you cannot explain.
Now we get to
that
watch this
well
again,
known.
Frank,
It's
to
technical.
see if you're
So,
right about
that's
this
too
cell.
complicated.
What did you say the other one stopped at?
So you waste your time when you
No,
mess with something like that.
that's that one.
Most of the stuff on
This
the
one.
internet, from those groups, are total waste of time.
9.5 volts also.
Okay,
It's not-
well then it
there's
should
not gonna be any
stop.
serious work come out of that in most cases. And
Then
some of
you'll
them
know
even build
that
it.
it's just the condition of the cell.
Absolutely right.
Yes,
They don't build it.
one of the.
Yeah, one of the cells is marginal.
Seems
That's
to-
not-
Well, that's what bothered me about those batteries
If you already know how
over
to do
here.
this, why are you
They,
asking me
the
questions?
cells,
You just do it.
I heard them,
Yeah.
that's what bothered me about these,
Well,
like number
here's
5
the
here,
big
Yeah.
one.
is it's very marginal.
Yes.
So I think
So-
So whatever's wrong with these batteries, that's why
Gentlemen, I'm
you
gonna
see-
shut the tape off.
And what is our amp hour, micro amp hour?
14.975.
Micro amp, okay.
Okay, so now we gotta switch, right, Frank? We don't wanna write it down, don't we?
Yes. But not
It's getting on down there now, so. it's probably
not
this
below
time to do it.
recovery.
Okay. Well, you know, the problem with these batteries is if you leave them in this condition, they may not.
When are we gonna start using bigger batteries, guys? Next time around?
After we,
Really?
No, John, on the next model.
yeah.
Are we gonna use a bigger battery?
Sure, car battery.
Okay.
Yeah,
Okay, John, could you step aside? I'll get a shot at you real quick.
okay.
Thank you, sir. So we're just about 11 volts on
Yeah.
that battery. Good. Thank you. That's the one you just took off.
Yeah.
Now it's the primary.
Yeah, I could have pumped a lot of water with this, Tom. Frank has to reset this every time.
Yeah.
What is that little box? Should we get one of those?
So we can get started.
Okay, you want me to?
Power analyzer.
Okay, go.
We should get one, huh?
Yes.
Well,
And
that's
he
good.
started it, time code says 16:08:35.
Well, there's not much left in them.
17 or time?
Yeah, I'm daylight savings still.
Okay.
Over here, thank you. And then our other big test is still waiting for this far battery to discharge, which could be another hour.
Well, no,
Well-
we are not going to
Okay.
fix that. Too serious.
Okay.
Oh, okay, thank you.
We're gonna charge this one, right?
So we have, yes, we are going to fully charge this one to be used tomorrow morning. So now we have
Okay.
second
What do we do with this one,
We-
Frank?
Good question.
Well, he's extra.
Yeah.
Save it, you might need it. If you have one cell reverse, you'll need it bad.
Did we already account for that other battery?
He's accounting the string, one string. He's gonna multiply that.
Okay.
So he's running the string right down, which is perfectly good. That's a good
Sure,
approach.
sure.
There's no need of doing exactly the same thing 3 times.
No, I agree.
But wait a minute now. We're running this string down.
Yeah.
But what about the 3 that it charged at the higher levels, right?
No.
'Cause
Well, he's
there's
taking
one.
it from there. He's taking.
Oh, I see what you're
those
saying.
three
I
and
see what
running
you're
the
saying. You can
string
get a
from
curve that
there.
way.
Then he'll just, the other 2 would do the same thing.
Does that give you a curve, Frank?
So, yes, this is 1/3 of what we
Yeah.
are going to
Instead of doing
experience.
the thing 3
with
times,
each
he's
of
just
them.
doing it once. And
Oh, I see. Okay.
it's an identical thing. If
Yeah.
you did it with the other 2, you'd be
Yes.
running the same
Then
thing.
he just plots his curve and boom.
Yeah.
But see, if you calculate all this time, you are over whatever the primary could supply in the first
It's
place.
the measurements he's making, which really are going to come out to us, the thing, but you can get a good estimate on the time, and the time estimate,
Right.
we're okay.
Yeah.
He's still got to reduce his measurements.
That's the hard part.
Yeah.
Getting it to that
And then
point.
as a control
You're
measure,
right
we are
about
going
this, Frank.
to
You're right.
fully charge one. So this is already
Well, see,
8, yeah. So somewhere
in this,
this one has a problem, yes.
and that was the primary that was running it to begin with.
Yes.
So one of them out of the package, didn't take any charge.
It's not surprising, the type of charge we're doing, as I said, is a little bit different from normal charging. And it depends on how they constructed that individual battery. If they got something a little too close, or didn't make it just right, then you can have that effect.
Taiwan.
Taiwan. Yes. Taiwan.
This is about what Garrett and I experienced with that one out there.
Yep.
11 minutes, down to 5, 5 and 5, 11, 11. That one's over there holding at 23.4. Just holding it. And here it goes smack.
So it should be around 7 minutes.
Oh no. 4 minutes. It's about right.
Altogether, 7 minutes.
Yeah, because you're depleting it right to 0.
Yep.
And I don't know how far you want to take them because you may not get a charge in them no more.
Should be, let's see, what's the worst case? No, we are going to stop after this one. It really doesn't. Probably we are running, then the battery's down. But shelf
Lovely.
Looks about right. 8 minutes.
So between 8 and 9 volts. This is where we are, where it's critical. So we might want to stop after this one.
Otherwise, we may not be able to recover, right?
Yes.
Right?
Yes, correct. So this will be our, this is our 6th cycle already.
Yeah.
So it goes down to
When it quits, right? 60 milliamps, 70 milliamps. Still gonna go a while.
yes.
About 8 minutes, 9 minutes, like you said, almost 10 minutes on that battery. Then.
Yes.
It's doing its thing with that battery, Tom. That one battery right there. That's good.
Is that the voltage at 8.07?
Yeah, but it's under a little different condition right now.
8 minutes.
They're gonna get one of those little meters.
Yeah, they're good.
Yeah.
Which one, Gary?
What was Frank
Power
Hensel right
analyzer.
here? Power
Single
analyzer.
phase power
Yeah.
analyzer. Voltec.
Or this one is also
Yeah, we need to pick those up.
yeah, doesn't give, of course, the features of this one.
Okay.
It's getting close.
Yeah, you're beginning to slow a little. It's
All
going,
right.
Frank.
Yeah.
Catch it. Stop it. There you go.
9 minutes. 1 second.
Oh, the battery's going back up.
That's the recovery, right?
Yeah.
Diminished load, now it's gonna recharge itself for a while.
It'll recover.
As long as it's going above 9 volts, we are fine.
Yeah, you
We
don't
didn't
wanna wipe
damage
them out.
it.
Yeah. Shouldn't have had any cellular reverse.
And here we are, 11 volts, so we should be fine. But we want to make sure that we charge them then regularly, so
Yeah.
that they kind of yeah, they haven't been charged normally, so we might want to charge all of them then.
How many hours has it been on that battery over there that we are?
Discharging through the
3 hours. Yes, 3 hours and 7 minutes. Yes, 3 hours and 8 minutes discharge.
That sounds about right, because you predicted 6:15,
Yes.
so that'd be about another hour.
Yeah, but it's not discharged at the rate I wanted
Correct.
to discharge it. So we
So-
just are going to use this battery tomorrow as a
Do we need to put
full.
one on the charge overnight?
Yes.
Yes, this one here.
Okay.
You want number 1 on the charger over
Might as
there.
well take it out of there, John.
Uh,
He's not gonna use that reading at all. Be sure that's true.
Frank, you're not gonna use that reading at all?
Well, let it go.
No, partly. I plotted kind of a curve in certain
Okay.
time frames at what current it was, so I can predict at least somehow how it's discharging.
Yes.
Yeah, but this would
It's not
be,
accurate.
this would be a discharge rate in a normal circuit,
Yeah.
not in an extraordinary normal circuit. In other words, something that's a controlled.
Yes, controlled discharge in order to get to deplete it to whatever until 10% residual charge is left.
Well,
So let's
I think
disconnect
it's
that.
way past 10%.
All right, that's gonna go on a normal charge now overnight.
Yeah.
Yes.
John.
Okay.
Frank wants you to use that tomorrow.
Stop here. So this was 3 hours and 9 minutes.
Okay, this battery here might work tomorrow, might not.
Got one?
It's about 4.5 volts.
Uh-oh. Okay, that may be a bit.
We took it down too low.
Yeah.
Let it go.
No, it's not supposed to be too low. So normally you could discharge it with 100 milliamps for 4 hours. And it's still,
Well, if that cell changed though during that discharge, that would explain why it's so low all of a sudden.
yes, could be that one of the
Well,
cells
can
is
you
maybe-
charge two, John?
Yeah.
Yes.
Maybe we better.
No, we're
charge
not
another
gonna
one.
touch this one.
No, let Frank tell you which one to charge, but maybe we better charge another one just to be sure.
We can.
We
can
know
charge-
that the primary has a difference in the cell.
Right.
So we wanna use the
this
two.
one. This one is the best.
No, that's the worst. This is the best.
Let's charge one just to be sure, so
Yes.
we'll be sure we got one. It's good tomorrow anyway.
I can charge two.
Okay.
So
let's
it'll
get
be
that one.
these two.
Yes.
All right, that'll work.
Okay.
I just wanna try something for my own edification, Frank,
Yep.
since I already know anyway.
Don't bring it down.
Well,
too
this
much.
one's already got one cell.
Okay.
Yeah, this is the one that doesn't run as long. It puts them over 9 volts. Right?
But maybe what we can do is really find out which cell is better.
Okay. I just want to see something. Okay, it's not there.
Let me
Okay,
check
here.
the cells, please.
Okay, it's at 5 now. Climbing up there. I just need these clips, huh?
You need to turn your meter off too, probably.
Yeah, see this one here, Frank? This one's here is already back up.
Okay.
So this is the best battery.
Number
Right.
3 is the best, okay?
Yeah, number 3, that's the one that ran the motor the longest
Yeah.
each time, not pulse charge.
Number 2 we haven't touched since the initial
Well,
charge.
this one here is the one we ran on the resistive load, which is below, well, it's just moving up to 5.5 now.
Well, if we're lucky, we didn't damage it, but we'll have to see. It's better to have 2.
Okay, so we're gonna push.
That way we got
Push the
a
current.
little bit of extra in case one poops out, we still got the other ones.
3.8. This one is a little bit low.
Which one? Right.
The first one.
Cell phones.
The rear- okay, let's mark that one.
Notorious for, you know, they're
So
Okay.
if we compare them,
charging
this
them.
has 3.8,
Cell
this
them.
has 3.8.
Sure.
Eight,
Or if you
six,
just charge a
this
little
one
bit too
is, 7.5.
low,
That accounts for the difference in the motor.
they can have actual physical damage
Right.
for sale.
That accounts for the difference in the motor.
We don't know what the sound
Let
really
me-
is.
let me-
It's like
Yeah, same thing.
charge, you pull them off and they're not charging, they're hot.
short.
No, you got a short in there, you might
Just
store
charge.
it.
See how it behaves. Well, this one is really questionable.
Yeah.
This one cell here. I put down a question mark on this.
I'll push the current to them initially to get them to a level. Then I'm gonna back down to about 250 million.
But still, these three, they are okay.
Okay.
They are okay.
Gentlemen, is there anything you'd like to say to the camera before I turn it off?
No.
Frank, you're up, buddy.
Yeah.
Coeur d'Alene's a great place, love being here.
Yes.
Okay,
It's
steaks
an
are good.
interesting, very interesting day. We have, I think, accomplished quite something. And yeah, now it's time to sit down and discuss the results, observation, and calculate a little bit and make sure that we haven't overlooked anything and come up with a good conclusion.
Good. Okay. Thank you. Okay, this concludes it. I'm going to shut the tape off till tomorrow.